This is Timothy Wood with Citadel Civil Engineering. This is CVIL202 statics. And in this lecture, we're going to talk about calculating area centroids using composite body theory. Most of you should be really excited about this because you weren't particularly excited about doing double integration in the previous video. This method allows us to calculate area centroids without having to use integration. It's exciting. So when we take a look at this, what we're going to do is we're going to start by remembering our definitions of the area centroid. We said that we're taking the first moment of area, so a perpendicular distance from the y-axis times the differential area, integrated to get the total moment about the y-axis divided by the total area. Or in this case, this is a moment about the x-axis. Our y distance is our perpendicular distance. For the first moment of area about the x-axis divided by the total area to find our area centroid locations, which if we're modeling shapes that are of constant thickness, constant density, and a uniform gravitational field, we can take all the way back to being an equivalent system of a total force acting at a point. This is how we would mathematically model a shape as a point, as an equivalent system. Now, integration, not exciting necessarily for most of us. Again, as engineers, we don't have to like math, but we do have to be able to do it. And so we can do this. We could bootstrap our way through this. However, if we remember the definition of integration, it's basically just the sum of the area under the curve. So we can think of this integration as not an integration per se, but as a summation of larger shapes. And if we do that, we'll get a composite body theory form of this equation that uses sigma for summation. So sum of the x times the total area divided by the sum of the total areas. Likewise, we're going to have sum of the first moment of area divided by the total area. The key here is that we're considering recognizable shapes. So if we have a body that's not made up of continuously smooth things, if you're a mechanical engineer, you're super excited about aerospace, you might have to always go back to double integration because you're going to do smooth shapes with continuous functions. But if we're looking at a body that's made up of rectangles and triangles and circles and things that we can calculate the areas and centroids of easily, we can use this method. And in fact, your FE reference handbook at the back of my abridged version has a table with a ton of areas, and it tells you the area and centroid location for each one of those values. Your textbook also has similar information inside the front cover. So we're going to recognize all these shapes. And if we do this, we can just do simple, straightforward geometry and then sum some things up and plug it back into this form of the equation. So let's look at our procedure for this. We'll work a problem together in class where we break down this shape and figure out where its centroid is. Our first step is to identify our shapes. So we got to break down and label our shapes. And there's a couple of different ways we can do that. So for example, if we were looking at this shape here, you might see a rectangle and a little triangle and a circle for the whole. That might be one way to do it. If you were thinking of it as a milling exercise, so for those of you who have experience in manufacturing and milling, maybe it's one big block, one big giant rectangle with a hole that is a triangle and a hole that is a rectangle and a hole that is round, okay? So those are all identifiable shapes. Lots of ways we could break it down, but you pick the ones you like and you identify those shapes. The next thing we're going to do is we're going to create a table of properties for these shapes. Okay, so a table should be putting us in mind of using Excel if we wanted to automate or at least help with the bookkeeping of a process like this, though we certainly don't have to. Handwritten solution is still totally fine. Now, when we think about this table of properties, what we're trying to do is populate these two equations. So one of the properties we're going to need is the area location. So the area, okay. And if we were thinking about our shape here, so if we look at this hole, this round hole, if we have holes, those are going to be negative. So if we have solid shapes, that is the positive area, and then holes are going to be negative area. So this area is going to be negative for holes. The next piece that we're going to want to identify is our centroid locations for those various shapes. And that's going to be those perpendicular distances. So those centroids. Centroids, X and Y. And that's going to be the centroid to each shape. So if we think about our rectangles, we'll go to the center of the rectangle. Now, the thing to keep in mind is that our table is going to tell us the center of the rectangle from maybe the corner of a rectangle, right? Or if we're thinking about triangles or circles, it's going to give us some reference point. But what we need is the centroid location back to whatever axis we're referencing. So we're going to have an origin, a coordinate system, and we need that perpendicular distance to the centroid from the X and Y axes. And if it's in quadrant 1, they'll be positive, and if it's in other quadrants, they might be negative, or depending on if they're on the negative side of the y-axis or the negative side of the x-axis. So our centroid values can be positive or negative just depending on where the centroid falls. And again, that's back to some common origin. Okay, so we'll make a special note on that. This is from the origin. Okay, so if we look back at our equation, we've calculated our areas for each shape. We've calculated our centroid location. And so in our table, what we'll want to add now is our first moments of area. This would be X times A and Y times A. And this is where Excel might come in real handy, because we could just set up this cell once and drag it down for all of our shapes and come up with all of our first moments of area. We're going to bring through whatever negative signs we would have for holes and whatever the sign is for our centroid locations. And what we're going to end up with is these 5 tables: area, X, Y, X times A, and Y times A, in a table. And that'll be great. The last step is then going to be to sum the columns. And then when I sum the columns, I'm going to get the total area when I add up all the areas. And when I sum the columns, I'm going to get the total moment about the y-axis and the total moment about the x-axis. And then from there, I can solve by substituting the total area into the denominator and the total first moments into the numerator, and solve for the X and Y centroid locations. And those equations, by the way, are all in your FE reference handbook. I look forward to working a problem with you in class, and I'll see you then.